Okay, so rational functions. A rational function, the word rational, remember, is a fancy word for fraction, right? Now, the difference between a rational function and a polynomial function with fractions is you can have a polynomial function, right, where you have 1/2 x squared, yada yada yada. There's still might be a fraction in here, okay, but the variable itself is not in the denominator. And so that's really the tip off. So a rational function is any function that includes at least one x term in the denominator. So we're looking at a rational function almost as two separate pieces, right? The entire function can be written as a fraction. That's what makes it rational. But we really look at the numerator and the denominator separately as their own individual polynomial functions, okay? So all of the stuff that we covered earlier in this unit, from uh, zeros and factoring and all of that work, that's still going to be applicable to this concept, okay? And I thought I would show you just some examples, some random examples. Well, not necessarily random. I put some thought into this about what rational functions look like when we graph them, okay? So I'm only going to activate these one at a time. So if you look at this first one, this is the function 1/x, okay? This is about as basic a rational function as you could possibly get. Now, notice we don't have to have any x terms in the numerator, but we do have to have an x term in the denominator to call this a rational function. And what you start to see in rational functions, and you'll see this in a lot of these examples, is this sort of swooping behavior like so, okay? You're going to start to see this over and over again, multiple times, in fact, in some of these examples. And what we do is we call this sort of behavior like so, I call it asymptotic behavior. So you can see as we move out towards here, the red line is really dancing on top of the black line, right? They're not overlapping. You can even, if you really zoom in closer, you can see a little bit of space here, and that space gets thinner and thinner, right? So when you talk about these rational functions, we start to see this, what asymptotic behavior is, okay? Because when you think about, and we're going to discuss this in a future video, when you think about, domain of a function, when you look at a fraction, we have to be very cognizant of what's in this denominator, right? We can't let the denominator of a fraction be 0. That's why you see this, this asymptotic behavior where x is 0. This is the line that represents all of the points that have an x coordinate of 0. And this graph, if we zoom up, is dancing right next to it as well. Even if we trace, you can see the x coordinate is not 0. It's really, really close to 0. And as we get really, really close and closer and closer and closer, we get closer and closer and closer to 0, we keep tracing, those y values are increasing. So we can see that behavior, and we're going to talk about what that means in a little bit, okay? But that's one example of what a rational function looks like. Here's the second one where we have just x squared in the denominator. So we see these two sides coming together up here, okay? And you can reason your way through this. Why don't we have the same behavior where this graph was coming down here with negative outputs, right? The y values were negative down here. We're not going to get any negative outputs from this function, because if we plug negative values of x in, the y values are going to be positive because we're squaring them. So that's why we see this asymptotic behavior sort of converging together from this blue graph up here. Okay. Now, once we start introducing x terms in the numerator and the denominator, okay, we start to see some really crazy behavior. So let's zoom out here so you can see this bigger picture. Okay. So now we would say that there are 3 branches to this function. We've got this piece over here, we've got this middle piece, and then we've got this piece on the right. You can see where the vertical asymptotes are here, right? You can see this vertical line at x equals -5, and you can see this vertical line at x equals +5 as being those vertical asymptotes. Again, that's got something to do with this denominator. We'll investigate that a little bit further, right? If I plug -5 in here, -5 squared is 25. 25 minus 25 is 0, so that's a no-no, right? Okay. Now let's take a look at a different example. So we can also have 2 branches of this function like so, and then this middle branch, if you will, sort of looking like an even function, right? With where it's opening up. All right, watch this. What if I change that -6 to a +6? The whole thing flips over. That's kind of interesting, right? Think about the implications there where we're taking the opposite of something and reflecting, and reflecting the graph over. Sorry about that. Okay, and check that out. So we've got this option, we've got this option, and we've got this option. All things, all branches in play here. We're going to cover a big swath of this graph depending on what the numerator and denominator look like. Let's take a look at this one. A totally different look. Okay, now I'm going to zoom out so you can get a better idea about this. Okay, now when you look at the characteristics of these two graphs, these first two that we looked at, okay, this third one here has a different characteristic than this second one, than this first one. And again, we're going to investigate this a little bit further, but we see here we have what's called a slant asymptote, okay, where it's got a line, a line that isn't vertical or isn't horizontal, but on a slant that is at where we see this asymptotic behavior as well, okay? And then we throw the final curveball at you where, all right, this graph, right, looks a little bit like this. When you see x squared on the top and x on the bottom, x squared on the top and x on the bottom, you had this behavior here, and then you get to here, where are the asymptotes, right? I mean, we could zoom all the way out. Why does this graph look like a straight line when all of these other rational functions looked anything but like straight lines? Okay, this one was a straight line. Kind of an interesting concept here too. And we're going to investigate all of this in some of these future videos. Just wanted to give you an idea about how these rational functions manifest on the graph physically. Okay, and it all is going to be determined by factoring. It's all going to be determined by domain. It's all going to be determined by these values of x. Okay, you can hear Evelyn going crazy in the background here. All right, I think I'm going to stop this one.